I'm Rachel Ryskin, and I'm going to tell you about probabilistic weighting of perspectives in dyadic communication. So I want to start by thinking about a very simple and fundamental question: why do we talk to each other? Usually it's because we want to exchange information. This means that most conversations involve some knowledge asymmetry between the speaker and the listener. This asymmetry is both the reason to have a conversation and also what makes it a challenge. Speakers and listeners have to keep in mind both their own knowledge and their interlocutors to avoid miscommunication or confusion. And this coordination process is exactly what we're interested in, and we're going to study it here by looking at the production and comprehension of referential expressions. We know from lots of past work that speakers and listeners are sensitive to their partner's knowledge state. Speakers tailor referential forms to the knowledge of the listener. So for example, speakers will provide longer descriptions when they're talking to someone who's a novice versus someone who's an expert on a particular topic. And listeners are sensitive to the knowledge of the speaker. So for example, eye tracking studies show that listeners are able to anticipate reference based on what the speaker does and doesn't know about. So if the speaker is asking a question, listeners look to parts of their visual display that the speaker doesn't know about. At the same time, there's evidence that the speaker and listener also consider their own perspective. So for example, speakers often implicitly reveal that their display may be different from the listeners, and listeners do still look at areas of their own displays which they know the speaker can't see. To account for the dual influences of both interlocutors' perspectives, Tailor et al. In 2016 proposed a multiple perspective model, which uses a weighted combination of probabilistic information about how referential expressions are mapped to reference according to both perspectives. And I'll go into more details about this shortly. In the rest of this talk, I will use this multiple perspective model to reanalyze an existing data set with the goal of answering two questions. One, how do speakers and listeners weight their own versus their partner's perspectives, depending on the role that they're playing in the conversation? And two, do dyad members adapt their weighting to the behavior of their partner over the course of the conversation? I'll start by giving a quick overview of the data set. The data here were previously reported in Ryskin et al. 2015 as part of a larger study on individual differences in perspective taking. We had 152 naive participants come in as pairs and engage in a referential communication task. Over the course of about an hour, they alternated between being speaker and listener. They were in separate rooms throughout and communicated through microphones. And we collected eye tracking data on both participants throughout the experiment. Here's what the critical production conditions looked like. The participants would see a grid, and one of the items would be in a green square. Here it's the banana. And their partner doesn't know which one is in the green square. The speaker has to get their partner to click on that same banana on their own computer. So in this case, they might say, click on the banana. There's no other banana in the display, so that's all you need to say. On the other hand, in the contrast shared condition, there's also a small banana that's visible to both participants. So the speaker would need to say big banana to make sure the partner clicked on the right one. In the critical contrast privilege case, the small banana is only visible to the speaker, as indicated by the fact that it has this gray background. So there's, again, no need for the speaker to say big. So here I'm showing the main production result from this study, the rate of using an adjective to modify the target by condition. You can see that participants almost always use the adjective when they're in the contrast shared condition, 98% of the time, very rarely, only 8% of the time in the no contrast condition. And the contrast privilege case is somewhere in the middle, pointing to the fact that speakers are considering their partner's knowledge state, but also not ignoring their own completely. Now for comprehension, the listener has to click on the cell that their partner tells them, and we monitor their eye movements. We're looking only at trials where the speaker produced an adjective. So for example, in the one contrast shared condition, the listener should identify the target very quickly because once they hear big, they know it has to be the big banana. There's nothing else with a contrast in the display. In the two contrast shared condition, it should be much slower because there are two possible big things here, the big banana and the big balloon. So they have to wait until the noun to disambiguate which it is. And in the two contrast privilege case, there are again two big things, but only from the listener's own perspective. The speaker doesn't know about the small balloon. So if they're taking that into account, the listener should identify the banana faster than in the two contrast shared case. And that pattern is exactly what we see. Here I'm plotting the proportion of trials with a fixation to the target. The filled circles are the target and the competitor is the unfilled circles, that's the big balloon. Over a time window starting 200 milliseconds after the onset of the adjective and ending 500 milliseconds after the noun starts. And they start identifying the target most quickly in the one contrast shared case in green there, and more slowly in the two contrast shared case in purple. And the privilege condition in orange is in between throughout this time window. So with those behavioral results in mind, we can try to apply the multiple perspective model, first to production and then to comprehension. In production, what we're interested in is the probability of producing a referring expression, for example, saying the adjective big, given what the object is. So the multiple perspective model says that this corresponds to the weighted sum of the probabilities across the speaker's perspective and the listener's perspective. And this parameter alpha s here corresponds to the weighting of the speaker's perspective. And so as a result, 1 minus alpha f is the weight of the listener's perspective. So when alpha s is closer to 0, this reflects a speaker who weighs their own perspective less. They are mostly considering the listener's perspective. Whereas when alpha s is closer to 1, this reflects a speaker who's more egocentric. They're relying on the listener's perspective less. In particular, what we want to know is how speakers and listeners are weighting their perspectives in this privileged condition of interest, where the speaker and listener perspectives differ in a way that's relevant to the speaker's choice of reference. So we want to find the alpha s, which would result in a probability of saying big of 0.66 in this case. To do this, we need to estimate the conditional probability of saying big for the speaker's perspective and the listener's perspective. From the speaker's perspective, this privileged condition looks just like the contrast shared one. So we might expect that the probability of saying big from the speaker's perspective only is 0.98. And from the listener's perspective, the privileged condition looks just like the no contrast condition. So here we might expect that the probability of saying big from the listener's perspective only is 0.08. So now solving for alpha, we get 0.64, suggesting that speakers are weighting their own perspective more than the listeners. So that's sort of interesting in aggregate, but we can also do this separately for each individual. On the right there, I'm plotting the probabilities of using an adjective in each condition by individual participant. And this is just meant to illustrate that there's clearly quite a lot of variability between participants. And so as you might expect, the individual speaker alphas are also quite variable, but most are clearly above 0.5. So again, speakers tend to be egocentric. But it's interesting to note that they get less egocentric over time. In the first half of the experiment, alpha s is 0.73, and in the second half, it's 0.57. So far, we've used the multiple perspective model to reanalyze the production data from a dyadic conversation task. We saw a lot of variability in how people weight the two available perspectives, but speakers seem to generally weight their own perspective more. But they tended to weight their partner's perspective more over the course of the experiment. So next, I'll look at comprehension. Reference comprehension asks a different question than production. It's asking, given that I've heard the adjective big, what is the probability that each object is the intended referent? So we don't have a measure of this directly in our data, but using Bayes' rule, we can rewrite this in terms of the probabilities of saying big, given an object from both the listener's and the speaker's perspective, and also the prior probabilities of each object being referred to in the first place, given both possible perspectives. And then we again have the same sort of alpha parameter, which controls the relative weighting of the two perspectives, except now I'm calling it alpha L because it's representing how egocentric the listener is. So in the next few slides, I'm going to sort of try to give a sense of how all these probabilities are calculated. And for the sake of time, I'm only going to go into detail for a few of the key values, but I'm happy to go into more detail in the question period. So looking first at the listener's perspective, you can see that I've removed the gray cells because the listener sees all of those. For the prior probability of each object being a referent, we want it to be mostly uniform, but there is this one object that they don't see, the one that's in black. So presumably you're much less likely to talk about something that's not there. So we just assign a very low probability to that one, 0.05, and then divide the rest by 7. Now looking at the speaker's perspective, those gray cells are now black because the speaker can't see what's there, including notably the small red balloon. And the formerly black cells are visible to the speaker. So I've put a question mark there to indicate that there's something there that the speaker sees. And so again, we assign 0.05 to things that they can't see and 0.14 to the rest. Now we can look at the probability of saying big for each of these objects from the listener's perspective. We know from the production data that for the big balloon and the big banana, this should be 0.98. And for a small banana or a small balloon, the probability of saying big should probably be 0. And then the singleton items are estimated at 0.2 based on an average of the rate of using big on the speaker's privilege trials and their no contrast trials. Because from the listener's perspective, they don't know which is which, so we just average those. And the logic is going to be the same for the speaker's side. These unknown objects where the question marks are estimated based on an average of adjective use for all trials. So now plugging all these numbers in, we get a set of predictions for how likely each object is to be the referent at each level of alpha L. So here we're just going to look at the target in the solid lines and the competitor object in the dashed line. At a coarse level, you can see that the predictions are consistent with the eye tracking data. The highest probability for the target is for the one contrast shared condition in green there. And across all levels of alpha, the target probability is lower for the two contrast shared condition. That's in purple. And you can actually see that the purple target and competitor lines are overlapping because the probability of the target and the competitor is the same for the two contrast shared condition. That's the case where there are sort of two big things. So after hearing big, you don't have enough information to disambiguate. And critically, the two contrast privilege condition in orange is in between those two. When alpha is 1, that means that the listener is completely weighting their own perspective only. Then the privilege condition looks just like the two contrasts shared, and there's no difference between the target and competitor. On the other hand, when the alpha L is 0, the listener is only paying attention to the speaker's perspective, and then it's the same as one contrast shared. So now, in order to try and estimate which alpha value actually reflects what listeners are doing in comprehension, we fit model predictions at each alpha level to the eye tracking data. So in order to do that, we first simplify the eye tracking data by averaging over the whole time window for each individual and each condition. And then we can find the alpha value that minimizes mean squared error when we regress those average gaze data onto model predictions. And in this case, it turns out to be an alpha L of 0.27. So what I'll be plotting here is just the observed average proportions of fixations by individual across conditions over the model predicted probabilities for that alpha L of 0.27. And you can see that this does an adequate job of explaining the variance in the data, which suggests that listeners are, to some extent, considering the speaker's perspective more than their own, because that alpha L is below 0.5. And they seem to do so all the more over the course of the study. The best fit alpha L in the first half is 0.43, and in the second half, it's 0.2. So now after applying this multiple perspective model to eye tracking data, we can update our previous conclusions a bit. As I mentioned before, we saw a lot of variability in how people weight the two available perspectives, but speakers and listeners both seem to weight the speaker's perspective more. And they also tend to weight their partner's perspective more over the course of the experiment, which suggests that they might be adapting potentially to the idiosyncrasies of their partner. But it's also, this data pattern is also consistent with the possibility that they're just adapting to the task in general. And so to address this, we want to try to examine within dyad dynamics next. So in this figure here, I'm plotting a sample of model predictions based on the production probabilities of 12 individual speakers rather than using the aggregate probabilities that I showed before. And this is just meant to illustrate that there's a lot of variability here. So it seems like listeners would do well to adapt to this variability in some way. So to see if they do, we can redo the same fitting procedure, but now we're going to use the partner's probabilities instead of the average probabilities. And again, we can find an alpha value that minimizes mean squared error, and that turns out to be 0.16. That model fit is actually a little bit worse here than for the model that uses only the aggregate production probabilities. So it might be that listeners are actually not adapting to the specific rates of adjectives. You might imagine that maybe it takes too long to accumulate enough data. It might be reasonable to use the aggregate probabilities instead. Another possibility is that listeners might instead be adapting more globally to how the speaker is weighting perspectives. Or in other words, they might be mirroring their partner's alpha S during production. So in this last analysis, we go back to the aggregate production probabilities, but instead of fitting an overall best alpha L value, we just use the partner's alpha S value and subtract it from 1 to get a dyad-specific alpha L value. So in this graph here on the x-axis, I'm plotting the predictions from models where the alpha L is 1 minus the partner's alpha S during production. And again, this accounts for substantial variance, but turns out to provide a less good fit to the eye tracking data than the aggregate model did. So to wrap up here, it remains unclear if speakers and listeners adapt to their partner's perspective taking performance despite all the variability between dyads. One important thing to consider is that potentially the absence of dyad-specific effects may just reflect that there's more noise in those models because they include individual level data. Another thing that might have contributed to this is that we chose to use an identity linking function between eye gaze and probabilities. And this is almost certainly wrong, but it has the benefit of making no other assumptions. So that's what we chose as sort of a first attempt. So one avenue for future work will be to investigate different potential linking functions. Another important avenue for future work will be to compare this multiple perspective approach to other frameworks. More broadly, most conversational exchanges happen because someone knows something that the other doesn't. Understanding how humans effortlessly coordinate these asymmetries is critical for the development of conversational agents, and seems increasingly important these days when so many of our conversations are no longer in environments like this one, where these women have many cues to the other's intentions, but are instead happening in much more impoverished scenarios like over Zoom calls. Thank you.